Start. Okay, so let's dive right in. Let's start with a little bit review of, we talked about defining, or what quantities were, defining quantities, and defining variables. So I have a scenario here. So let's watch this video, and this is going to give us kind of a situation to think about lots and lots of quantities. And we want to specifically think about distance quantities and time quantities. Okay, distance quantities and time quantities. What I'm going to have you do, I'll show it to you a couple times. I'm going to have you break off, and you're going to brainstorm and come up with, in terms of distance quantities, we want 3 that are constant in this situation, and 3 distance quantities that are changing. And for those changing ones, we actually want to define variables. And then similarly, we want 3 constant time quantities in this situation, and then 3 time quantities that are changing, and we want to define variables for those. Okay, so we'll watch it a couple times, and then I'll set you loose. So just back to here.
Left.
So there's lots of opportunity. We'll show one more. Lots of opportunity to think about all different kinds of distance quantities, constant and changing. All different kinds of time quantities we can define, constant and changing.
Left.
Another one of my exciting videos. All right, so I'll show you here. So this is our goal. Running through the tunnel. Distance quantities. Name 3 constant distance quantities, and then come up with 3 changing distance quantities, and actually we'll define variables for those. Come up with 3 constant time quantities in this situation, and 3 changing time quantities. We're going to define variables. So in terms of being specific, right, we said one of the very important things about these definitions of quantities and variables is that we're fully specific. With distance and time quantities, being fully specific means reference point. What's the starting location? What's the starting reference point for the distance being measured? And also for time, what's the starting time reference point for measuring an amount of time? So that's part of specificity when you're talking about distance and time. You've got to have that initial reference point for both distance and time quantities. Okay, so get a partner, brainstorm together. You're coming up with 12 different quantities. And I'm going to take attendance. Oh, let me, so it again.
Left.
Okay, so let's just do a couple, and then I'll give you some more time once we do them. So let's see here. Where is Fala Nida? How do I pronounce your first name? Nada. Okay, how about a constant distance quantity, Nada?
Distance between beginning of tunnel and end.
Distance from the start of the tunnel to the end. Okay. How'd she do? Does she need a unit on this? We're defining a quantity, just a quantity. Remember we talked about this last time. Quantity is just that measurable attribute. It's just a distance from me to the skateboard. The quantity is that distance. Do we have anything to do with numbers yet? Nothing to do with numbers, so it's okay. So when you're just talking about a quantity, and you saw this all throughout the web work, when it's talking about quantities without units, that's okay. When is it when we need units? When we define a variable, because a variable takes on values of the quantity, it takes on numbers. So with a variable over here, we're going to need the units. Okay, was she specific enough? Distance from the start to the end of the tunnel. Yeah, is it constant? Does it change? No. Good job. All right, so where is Flora? Okay, tell me another one. Where's Flora? Oh, there you are. I'm looking for a constant distance quantity in this situation. What's a distance that stayed constant in this situation? Can you think of one? All right. How about a changing? So let's go over here. So did you think of a changing distance quantity? The distance from the woman to the man. All right, what do we want to call that? Let's just call that little d. So we'll say d equals, or d is the distance from the woman to the man. What do you think? How'd she do? Now we need units though, right? Because we're saying it's d, we're saying it's a number. So, in? What do you want? What unit do you want, Flora? What could we measure from the man to the woman? I heard someone say feet, so we'll do feet. Okay. How about another changing quantity? Where is Matthew Western? Matthew Western here? There he is. How about another changing distance quantity? Okay, so distance covered since entering the tunnel. Distance covered since entering the tunnel. How is that? So we'll call that one x, say. X is the distance covered since entering the tunnel. So let's review our three criteria for defining a variable. 3 criteria. First criteria was, it's got to be, remember? Specific was number 2. What was the very first thing we said about defining a variable? Remember? It's got to be a quantity. It's got to be a quantity, not an object, not anything else. It has to be a quantity. How do we do it? So distance covered since entering the tunnel. Is it a quantity? Is it a measurable something, right? Yes. Second is it specific enough? Distance covered since entering the tunnel. Is it specific enough? I don't think so. I'm not sure what this means. Why am I not sure what this means? Okay, so tell me. Right. So which person? Which person? You got to know which person you're talking about here. Distance covered by who? Right? So he wants the man. Now, is it specific enough now? Do we know exactly what we're talking about? X is the distance covered by the man since entering the tunnel. Okay, that's number 3. So we still need units. What do you want to do, Matthew? In meters. Okay, great. Okay, getting the hang of this? Does that make sense? So now that we've done a couple examples here, do you want to keep going? So I'll give you like a couple more minutes while I start taking roll. You can keep going now that you've seen some examples. Okay, so there's always one who asks. All right, let's do one more constant distance quantity. Where is Colleen Sullivan? Tell me one more constant distance quantity that came up with. Okay, so what do we think? Is it a quantity? Is it specific? So so I'm not sure if you're talking about the race or the video. So, okay, so the actual race. So maybe if we said the start of the race to the end of the race, would that do it for be specific enough? Now I think now I'm pretty sure, or I'm very confident of what that is. Okay, let's do. How about a constant time quantity? Where is Scott Volker? Constant time quantity. Time from the start of her run to the end of the tunnel. How do you do? So start of a run. Start of the video or start of the race? Well, okay, so that proves the point that you got to be specific. It could be either one. So which one do you want? Start of the video. So the time it takes from the start of the video to start of video to, and you said her, so you're talking about the woman, to when the woman reaches the end of the tunnel.
Would you have to specify women or man, or could you just put letters?
What do you think? If we want a constant time quantity, we need. So can we just say runners there? Yeah, they cross the end of the tunnel at different times. So you've got to specify which one you're talking about. So yeah, so because that's two different constant time quantities. So we want to be specific. So time from the start of the video to when the woman reaches the end of the tunnel.
Is that like saying that her speed was faster than his because she got out of this one? Is that kind of sort of leading towards that? Is that the reason why? Because they finished at different times?
Yeah, they cross the end of the tunnel at different times. So if you don't say who you're talking about, then you don't know which constant time amount you're talking about. The time for her to reach the end of the tunnel or the time for him to reach the end of the tunnel. It's two different things. So you don't know for sure. And that's the whole point of defining these things. You want to read that and know for sure exactly what quantity you're talking about. Does that answer it?
So would it be the same thing for distance? If you were to phrase that question, you have the distance ran from the start of the video for the woman until she reached the end.
Exactly, because her distance to the end of the tunnel would be different than his distance if they didn't start exactly in the same place. And I don't think they did. I think she was behind at first, right? And then she passed him and was ahead. So yeah, at the start of the video, they are two different distances from the end of the tunnel. So you'd have to specify which one. All right, one more constant time quantity. How about Laura Rodriguez? Where's Laura? Wait, I already called on you.
Yeah.
Oh, you thought I was saying someone else. Okay, I said Flora is what I said before. Are you Flora or Laura?
No, Laura.
Where's Flora? Oh, thought she got away with it. Okay, so you're off the hook. You've already answered. So how about another constant time quantity? Flora. Time to run through the tunnel. How'd she do? Is it specific enough? Okay, why not? Change it. Yep. Now we got it. Time for the man to run through the tunnel. So I kind of abbreviated that. Okay? And I like your version better. I'm not going to clear it, but she's a little, so mine's a little bit loose there. So time for the man to run through the tunnel. It'd be better to say what she said. From the start of the tunnel to the end of the tunnel. Okay? Just so that's really clear what the starting and ending point is. Okay, changing time quantities. Okay, so these are maybe the most tricky. So where is Alexandra Cohen? Okay, how about a changing time quantity? And we'll define a variable for it. T equals?
The time elapsed from when
What's that?
Oh, in seconds.
Time elapsed from when the woman starts the race in seconds. What are our three criteria? First criteria, variable's got to be a quantity. Second criteria, it's got to be specific enough. Third criteria, it's got to have units. We're going to do this all semester because it's about when you get to problems, the students who learn to attend or pay attention to the quantities and know exactly what they are, you're going to succeed. So we're going all semester we're going to practice this. Okay? So because this is, like we said, this course is all about quantities and specifically changing quantities. Okay? So in problems, it's not about trying to memorize a set of steps. It's about paying attention to quantities, especially changing quantities, and learning how to analyze those and draw conclusions. Okay? So how do we do on this? Time elapsed from when the woman starts the race in seconds. Thumbs up? Okay, we'll do one more of these. Where is Brittany Hale? Okay, Brittany, you're up.
The time pass of the woman, where's the time elapsed in seconds since the woman passed the man?
Okay, so what variable do you want to call that? So we've got to pick a letter.
Oh, T.
I already used T. Sorry. F? F equals the time elapsed in seconds since the woman passed the man. How'd she do? Meet all the three criteria for defining a variable? Absolutely. It's time elapsed is a quantity. It's nice and specific since the woman passed the man, and we got in seconds in there. So really, being this specific and this nitpicky is what allows you to have success when you're solving problems, if you're paying attention to the quantities and how they're changing. Okay, sheet. So let's look at, I want to look at this right here. Can you read that in the back? That it says Z equals used smartphone memory space in gigabytes. So I'm defining a variable. Used smartphone's memory space in gigabytes. How did I do defining my variable? Is it a quantity? Used memory space. Is that a measurable quantity? Absolutely. Is it specific? Yeah, so we got some smartphone here. We want to know how much memory is used up on that smartphone. I got my units, gigabytes. Okay, so I did a good job here. Hopefully I would be able to, right? So then I'm showing this quantity visually. And so this red bar, does it look red? It's supposed to be red. This red bar, black bar, dark red bar, is showing the current value. Remember what's the idea of a variable? It's that it what? Takes on any and every value that quantity could assume. So that Z at this moment, it stands for the value what? We'll just guess. 3.8 gigabytes. Currently, the phone is using 3.8 gigabytes of its memory space. That's what that illustration is showing. Make sense? Okay, and then later on, now, so what Z can take on many values. It's a variable. Variables vary. Now Z has the value of 7. 7 used gig on the smartphone. And so this is a visual representation of that variable Z that can take on many values, many amounts of used memory space. Okay, I want to show something else. Is that blue? On the same scale, I'm showing now a blue bar. that starts at about, so I'll let you, it's got a starting point and an ending point. We're only talking about the quantity that's represented by z. We don't have any other quantities involved here. Okay? So we've got, so what might that blue bar represent? If the red bar is the total used memory space, the red bar represents the value of z, then what could that blue bar possibly represent? If the red bar is the value, the current value of z, and the blue bar might be what? Yeah. Okay, she's saying it's the amount of photos, or the memory taken up by the photos. Okay. All right. What else could it mean? Is there any other? So yeah. So then we could say music and video and those things. Okay. So, but like, other than a specific type of thing on your smartphone that it represents. Any other ideas on what that? Yeah.
How much space is used between 3 and 5?
Okay. Yeah. So that what is so there's this like it was 3.1, and then it's kind of like a starting amount, and then like 4.7. So that blue bar then represents, what does it represent? Okay, so it represents a change in Z, a change in the amount of memory used. And according to the way I've estimated the beginning and end of the bar, what is the change? What is the change in gigabytes that's being shown by that blue bar? Yeah, the amount of change. What is the value of the change according to my estimates of the start and ending point? And how did you get that 1.6? Yeah, you're going to take the final value of the quantity minus the initial value of the quantity, and that's going to give you 1.6. The way that we denote a change in a quantity is with a delta sign. Delta, so you say delta Z. So it's a new, this is a new, you think of this whole thing as a new variable. It's related to Z, but it's not Z. It represents some change in the amount of memory. In this case, the change starting at 3.1 used up to 4.7 gigabytes used. So its units is also gigabytes. And we use delta to mean that amount of change. Okay, and again, to calculate it, should just feel natural. Starting amount, or sorry, final amount of the quantity. So you say Z final minus Z initial. That calculates the change. Okay, so the amount of change in a quantity is a hugely important part of calculus. And that's why we're going to be doing a lot of it in pre-calculus. Okay? So, now I'm going to move that blue bar, and now it is here, starting at 0 to 1.6. What's delta Z now? What's delta Z now? Is it the same or is it different? Is it the same or different? Okay, well, so it's kind of a toss-up, because what do we mean? The value of delta Z, the actual number, same or different? But what I'm representing now with this is a different change of 1.6. Okay, so to talk about a change in 1.6 gigabytes it's kind of not enough of the picture. That 1.6 gigabytes, that change could occur anywhere. So I can slide it. There's a change of 1.6. There's a change of 1.6. And I could put it right here at the end. So, right there. Still a change of 1.6. Pretend. It kind of looks like 1.5, but so we're calling it 1.6. In this situation, what might a real world version of this look like? So the red bar goes to 7, and starting from 7 is change in Z of 1.6. What might that be if we could think about just the smartphone? What might that be like? Any ideas? Just if you put kind of a real world twist on it, yeah. Okay. All right. So in terms of okay, so the memory that's being used at the moment. So you're saying you're going to start using an app, and that's going to take up 1.6 gigs to run that app. Is that what you're saying? Okay. Yeah, that's good. What else might it mean? Yeah.
You update your operating system. It will show you how much memory would potentially be taken up, so you can decide if you want to do it or not.
To download something? Or
yeah, to either download an app or update your OS.
Okay. What about actually doing it?
7 gigs, and then before you click accept or whatever, it will show you on your meter how much
more it's going to
it
require.
would be like the 1.6.
Okay. And how about actually doing it? What about actually saying, okay, I'm going to do it? Yeah. Then so it's like you had 7 gigs on your phone used up, and you want to download something new, and what you're downloading is 1.6 gigs, and so that's going to cause a change of 1.6. So then the new after you're done, then the new value of Z would be what? 8.6. It would be the initial value of Z plus the change in Z would give you the final value of Z. Okay, so that's another important thing here. So new Z, another very important concept in calculus. New Z equals old Z plus what? Change in Z. Should make perfect sense. Your new value of Z would be what the quantity was before, plus how much it changed. In this case, you'd be saying 7 plus 1.6 equals 8.6. Okay, what about this? So let's... Oh, really? There we go. Okay, so now I'm going to tell you that this is Z initial. And this, in terms of the change, is Z final. Okay, I'm going to keep taking attendance. I want you to make sense of that. Okay? So every time before, the left side of the bar was initial Z, and the right side of the bar was final. Now I'm going to say Z initial is the right, and Z final is the left. So in terms of Z and delta Z, I want you to make sense of this situation. Talk with the person next to you. Where is Jesus? Okay. Vince, take it away. So, what did you talk about? So in terms of Z and delta Z, what's going on here?
Z initial, where it started, and Z final.
Okay. So can we put some numbers on this, or talk more about maybe what's happening, or put some values on it? I'm going to say 2.3, okay? And? You may have slightly different estimates. So final 2.3, initial 7.2. Okay, someone take it from there. Let's talk more. So what's happening here? Where's Shannon Davies? Yeah.
Would you like subtract the 7.2 and the 2.3?
Okay, and you're calculating what? Or change. So change in z equals? Tell me what I would do, not just the final answer.
Well, you would subtract the 7.2 minus the 2.3.
7.2 minus 2.3?
Yeah.
Is that right? This is the final now, right? The final is 2.3. So it's going to be? Minus? And what do we get when we do that? 4.9? What's this about? Does it make sense? What is negative 4.9 about? What's going on here? Which direction? Okay. So yeah. So on a number line, we think of right as positive, left as negative. That's true. Okay, deleting memory, deleting space, or deleting memory on your phone, or maybe a crash. Right? This case looks like a lot of memory is going away. Right? So what about what about the negative? Is that uncomfortable, or does it work in the situation? It works. Why? Because the amount of memory is going down. It's decreasing, right? And so when you have a decreasing quantity, your change is negative. It makes sense, right? And when you have an increasing quantity, the change is positive. Negative change means decreasing, in this case, decreasing z. So you still follow z final minus z initial, and it just works out. When it's decreasing, that difference will be negative. When it's increasing, that difference will be positive, and so that negative and positive gives us more information about the change in the change in the variable, the change in the value. If it's negative, that value is going down. Or it went down. And when it's positive, the value goes up. Okay, questions on this change. So we want to now distinguish between the value of a variable itself and the value of the change in that quantity. All right, and so those are two different variables. So we think of this as a different variable than z. And we know in negative 4.9 gigabytes, it could occur there, or we could reason about it somewhere else. We could have negative 4.9 down here, or down here. Okay? Doesn't have to, so its location is kind of mobile. So where it's occurring could be different, even though it retains the same value. Questions about the change in a quantity? All right, so let's put that to practice here in a situation. Okay, so in the fall, Labor Day is coming up, but I guess it's Martin Luther King. So we're going to have a Martin Luther King Day barbecue. And we're going to buy chicken, which costs $3 a pound. So what is a potential quantity we could talk about here? We need to buy chicken, which costs $3 a pound. So what might be a relevant quantity in this situation that you could think of? What's that? Number of pounds, right? Number of pounds. And so actually, that's what I put right here. I said total weight of chicken to be purchased in pounds. How did I do defining that variable? Is it quantity? Specific? Got units? Those are our three criteria. Okay, so what is y going to be? So what would be an obvious choice for a different quantity y? Any ideas? Yeah?
The total cost of chicken in dollars.
Total cost of the chicken in dollars. You read my mind. Cost of the chicken in dollars. Okay, so I'm defining x as the total weight, and y is the total cost. And I need to reference something here so this works correctly. Thank you. All right, so I'm going to buy, so X can change, right? X is a variable, it can vary. I can choose to buy different weights of chicken. So I'm going to buy 1 pound of chicken. So now, right now, X equals 1. What does Y equal? So easy, right? And look, so now over here, we're going to show a graph. So when X equals 1, Y equals 3. And so that is represented by a point. This axis is going to be X, which is total weight. And this axis is going to show the cost, Y, cost in dollars. And so that point right there, what it is giving us two values that correspond. It's saying that when you have 1 pound of chicken, you pay $3 for that chicken. So that point is showing the values of two quantities that correspond. Okay? The variables vary. Now X is 3. Instead, oh, that's not enough for my party. I need more chicken, so I'm going to buy 3 pounds. What's my cost? 9. Get a new point. So this is my initial point, 1, 3. And so here's the new point, 3, 9. That point represents the values of these two quantities taken together, right? It represents both a 3 and a 9. 3 pounds and $9. Now X is 7. Cost of the chicken, 21. Third point, 12. How much will 12 pounds cost? $36. So now we're starting to collect some points. Each one of those points represents a total weight and a corresponding cost. So it seems so easy, but it's my experience that students can't explain that very well. Students can't explain that very well. What does a point on a graph mean? It means two values that correspond, that taken together, of two different quantities. You got a quantity on the horizontal axis, you got a quantity on the vertical axis. So this point right here, what does it mean? What does that point mean? How about, where is Jeanette? Jeanette, what does this point that I'm pointing at right there mean? What does that represent?
I would say that if the weight of the chicken is 7 pounds,
Uh-huh.
the total cost is going to be $21.
Good. Yeah, so that point is those two values that correspond to each other taken together. The cost, or the number of pounds, 7 pounds, along with the corresponding cost, $21. And that's what that point shows or represents. Okay. Are these the only possible points? Are there more? How many more are there? There's lots of ways we could do this, so let's just do this. Okay, here's lots of points. Lots of choices, right? Variables vary. X can take on many different amounts of weights, and that's shown on this x-axis. And then once you pick a weight, that cost is determined, and the y-coordinate of that point is the corresponding cost. Is this all the points? Are there more? Lots more. There we go. So now that I'm plotting more and more points, what is taking shape? Or what do you see? Okay, a line. So a line is an example of a graph. Okay? What is a graph? When you see a graph, what you need to think is this. What does the graph represent? When you see, in this case, a line, when you see that line, this is what you have to think of what it is. What does it consist of? Points. Points. It's not a wire that you bend and move around. Okay? It is composed of points. It's just a lot easier with the way you're used to seeing graphs. It's just a lot easier to draw this. That's quicker and faster. But what is it really showing? It's really showing many, many, many points. So for instance, on that little graph I drew down there, I'm going to do this, 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 and let's do the origin too. How many points on my graph? How many points? 5 points, right? On this graph, there's 5 points. No, you missed the point. How many points are on that graph? An infinite number of points. All I've done is highlighted some of them. All I did is I said I want to focus on these 5. When you see a graph, when you see a line or a curve on the axes, you have to change your thinking about that. What that is a set of points that we can draw it easier with a straight, but just swiping our pencil. That's an easier way to draw it. But the way you think about it is this. Okay? It's really important. And those points emerge as the number of pounds increases. We get the corresponding cost for each number of pounds, and so that graph emerges. All the points emerge, starting from 0, 0, up to as much weight as we're going to put on a scale. Okay. Now I've got some more variables over here. Let's see here. So I want to get rid of these now. That's good. This. Okay, I'm going to focus back on those initial, these 5 points. Okay, so 1 pound, 3 pounds, 7 pounds, 12 pounds, and 0 pounds. These are the points for those. But we know there's many more in there. And let's just go ahead and draw the graph. See if I can do it well. Okay, that's supposed to be all one straight line. Let me try again. Have the technology do it. I know what I'm doing here. I do know what I'm doing. I'm a professional. I already did that. Right, right. Getting closer. There it is. Okay. Phew. All right. And so that can continue on. So, how many points on the graph? Infinite number. There's not just 5. There's an infinite number of points there. I'm just highlighting 5. That's the way you should see a graph. So now I want x to change from, talking about changes, 1 to 3. So I want you to finish the rest of this table. So then y would change from what? If x changes from 1 to 3, then y changes from 3 to 9. What is delta x in that situation? What is delta x? The change in the total weight. What would the change in total weight be? 2. Final minus initial. 3 minus 1 would be 2. And then what's the corresponding change in cost? 6. 9 minus 3. More space here. Okay. Let's do it again. And so how can we represent this on the graph? So how can we represent x changing from 1 to 3 on the graph? Just like when we talked about the gigabytes example with the variable z. How can I show x changing from 1 to 3? Let's see here. How about Jessica Joyner? What am I going to highlight?
Points from 3 and 3.
So this point?
No, 1 and 3.
1 and 3, these 2 points. Okay, so if we're changing from 1 to 3, then how can we, if I start here, how can I illustrate that change? Yeah, so going which way? Yeah. Up? So if I'm going to do a change in x from here, I'm going to go up. Is that right? Change in x goes this way. Just the change in x. So this is our x, is our horizontal. That's our pounds. And y vertical is our cost. So if we just want to change in x, we're going to go like that. And that's delta x of, and equals 2, because I went from x equals 1 to x equals 3. And when we did that, what happened to the change in y? We're going to, that change in y is vertical. We could show it there. And that change in y was? It looks like the change in y is less than the change in x. What's going on there? Shouldn't it be 3 times as much? Different scales, right? So this automated graph just gave us different scales. That doesn't phase us at all, right? We just recognize that a number of pounds this way is going to be different than the cost in dollars this way. There's just a different scale. Okay, so this is representing a change in x from 1 to 3 of delta x equals 2, a corresponding change in y from $3 to $9, which is a change of $6, and that's how we can show it on the graph. This is pre-calculus. This is all in calculus here, so we got to understand this. All right, so 1 to 7. I want you to finish it. So how would you finish the row, and how would you represent it on the graph? Go. Finish the row, represent it on the graph. A change of x from 1 to 7. Okay, where's Justin Kessler? Justin, talk to me. Y changes from? Did you change your mind? From what to what? Y is going to change from what to what? 3 to 21? I think. What happened? I have to do it again. All right, and what's delta x? Delta x is 6. Delta y? 18. And how can we show it on the graph? From? Starting at 7? Starting at 1. So we're starting at the same point again. Going to 7 to the right. And then? Going up. So now this is delta x equals 6 more pounds of chicken. Started with 1, 6 more pounds, ended at 7. right? Delta x equals 6. Then, when that happened, what happened to the cost? Went up, how much? 18. Okay, what about this? Go. So, butcher had 12 pounds of chicken on the scale. Wait, just got a call from my in-laws. They're not bringing their whole family. Only need 3 pounds. Go. So, x changes from 12 to 3. Go. Finish the line. And then how are we going to represent it on the graph? Where's Danielle Smith? Danielle, over there. Okay, how'd it go? So, y changes from what to what? -36 to 9. And delta x is? -9. And delta y? What is it? -27. This is what she said. Is it okay that they're negatives? Does it make sense? Why does it make sense that delta x is -9? I got 2 minutes, folks. Sorry. Don't pick up. Delta x is negative means it's a decrease. And so that's a nice thing. It tells us, oh, we got a change that's a negative. I know that it's going down. The amount of chicken went down by 9. Same thing with the cost. When the pounds goes down, your cost is going to go down too. It's going to go down 27. Okay, so when you look at these numbers over here, comparing the change in x to the change in y, and you look at these numbers, what kind of relationship do we have over here? 2 and 6, 6 and 18, -9 and -27. Remember from junior high. What's that all about over there? 2 and 6 taken together, 6 and 18 taken together, -9 and -27 together. What principle is that? Starts with a P. Starts with an R. PR. It's not probability. Proportionality, right? Certainly a prerequisite of this course. Proportionality. You've got proportionality. Look, we got proportionality of the changes. And what did you do when you solved proportionality problems? You set up what? Ratios. So I'm going to set up the ratio of delta y to delta x. And what happens? Doesn't it stay constant? At what amount? What we have is proportionality of changes in two quantities. Proportionality, listen to this carefully. Proportionality in the changes of two quantities. That is what it means to have constant rate of change. Proportionality of the changes of two quantities. Proportionality of the changes in two quantities gives us constant rate of change, and so the graph turns out like, how will the graph turn out? A line, straight. If you have proportionality of the changes, you get these similar triangles, and all those points follow a line. That's constant rate of change. Okay, remember, you got homework. Everything will be updated by the end of the day.